let's go ahead and talk about Chapter 4, which is the structure of the atom. Let's talk about the beginnings of the atomic theory really quick so you know the important things to remember about this. Democritus was the first person that we have on record helping us contribute to the modern model we now have. He suggested that the universe was made of tiny units called atoms, and he also told us that they were indivisible, that these were the smallest units and that we could not divide them any smaller than they already are. Aristotle came on the scene, and instead of matter being made of atoms like Democritus thought, he believed that matter was made of earth, fire, air, and water. Eventually, obviously you know that this was disproven, but this is what Aristotle believed at one point. John Dalton came on the scene, and he did agree with Democritus that all matter is composed of atoms, and that atoms of the same element are alike. So if I have a boron element, then that element is made up of boron atoms. Now, atoms of different elements were not alike, and they could join to form compounds. So, for instance, beryllium and fluorine, they're going to have different atoms because they're different elements, but they could join to form compounds, and they're going to do this in whole number ratios. For instance, I'm not going to have half a beryllium to one fluorine. It's always going to be 1 beryllium to 2 fluorine, and having whole number relationships like that in ratios. Now, in a chemical reactions, Dalton also helped us know that atoms are separated, combined, or rearranged. They're not lost, and you don't create new ones or lose any. They're just separated from each other. They're combined to make a new compound, or they're rearranged. Now, J.J. Thomson, he actually accidentally discovered electrons, and so he developed the plum pudding model. A way to think about the plum pudding model is a blueberry muffin, because we don't really eat plum pudding. But a blueberry muffin, in a blueberry muffin, the blueberries are randomly placed. They are not in one order every time. They're always random. That's what he thought about electrons. He thought electrons could be anywhere in the atom and that they were all randomly placed. Rutherford came along, and he actually discovered the nucleus because he found out that most of the mass is at the center of the atom, so he discovered that there was a nucleus in the center. He also discovered protons. So he disproved the plum pudding model because he determined that the nucleus was positively charged because of the protons, and that meant electrons couldn't be randomly placed because they could not be in the middle or the center of the atom. He also determined that electrons must orbit the nucleus. Now, Niels Bohr was the next scientist we're going to talk about, and he actually, instead of just orbiting the nucleus randomly like Rutherford thought, he actually determined that electrons existed in set orbits, that there were set orbits that they had to travel through around the nucleus. He also determined that valence electrons contributed to the chemical properties of an element, so that the number of valence electrons, or the number on the outside orbit or level, helped us determine what type of chemical properties an element had. Then James Chadwick is the last scientist we're going to discuss, and he discovered the missing part of an atom, which was the neutron, because they still had a little part that the mass was not making up for them, and so they knew there was something else, and he discovered that we had neutrons. So that is the history that you need to know about the atom. And I just want to touch on that for just a minute before we start about the structure of the atom. Now, let's look at the modern model. So all of those people helped us come to this modern model, that all atoms are made up of 3 subatomic particles: protons, neutrons, electrons. The nucleus is composed of protons and neutrons. This model no longer assumes that electrons orbit randomly. They assume that they have to be found in certain energy levels. And we also know now it's all impossible to know the exact location of an electron. We can know the probability, but we can't know the exact location. Now let's look at the atom. The atom, which you already know this definition, but it's the smallest particle of an element, and it retains the properties of that element. They're made up of various subatomic particles, and the 3 subatomic particles are distinguished by mass, charge, and location. Now, proton is a positive charge, and the proton's purpose is to identify the element, just like DNA is for a human. If we need to determine who did a crime, we use their DNA that identifies which human did it. That's exactly what protons do. The number of protons never change, and it tells us which element we're working with. Neutrons, they have no charge, and their purpose is to stabilize the element. If you have too little or too many neutrons, then your element is unstable. The electron has a negative charge, and the purpose of it is to determine the chemical properties. And so it tells us, the number of electrons is going to tell us what type of chemical properties an element has. Now, you need to jot this chart down because you need to know these things. You need to know the symbol for each one. You need to know exactly where they're located, their charge, and then the main thing you need to remember about their mass is that electrons are much smaller than protons and neutrons. And as you can see, protons and neutrons have very similar mass. So they're very similar in size, but electrons are teeny tiny compared to them. Now let's talk about the nucleus a little bit more in depth. We know it's at the center, and we know it's made of protons and neutrons. So therefore, most of the mass is found in the nucleus, because remember, they have much larger mass than electrons. So if we have protons and neutrons together, then most of the mass is going to be found at the center. The nucleus has a positive charge because protons are positive, neutrons are zero charge. So that means a nucleus is always positive. Now, a little bit more about electrons. Electrons orbit around the outside of the nucleus at certain energy levels. We already knew that. And the mass of the electron is much smaller than that of a proton and neutron. So we have discussed that, but just a reminder. And in our Chapter 5 video, we'll actually talk about electrons the whole time. So we're going to dive more into them a little bit later. Now let's look at atomic number. The atomic number is the number of protons, and this number is found at the top of the element symbol when you're looking at a periodic table. Each element has a certain number of protons. The protons never change. If you have 4 protons, it's always beryllium. If you have 3 protons, it's always lithium. They never change. If you change the number of protons, you change the element. The atomic number also equals the number of electrons. So if beryllium has 4 protons, it also has 4 electrons. Now let's look at mass number. The mass number equals protons plus the number of neutrons. So they're added together. So if you need to find the number of protons, you're going to say the mass number minus neutrons. If you need to find the number of neutrons, you're going to say mass number minus number of protons. The mass number is the number underneath the element symbol, and it's usually in a decimal, like you have decimal places after. It's not a whole number, but what you can do is round it to the nearest whole number. Now, that number is also called an atomic mass unit. We usually do not use grams or pounds to measure an atom. It's much more convenient to measure them with atomic mass units. So 1 AMU, or atomic mass unit, is about the mass of 1 proton or 1 neutron. Therefore, if I have 4 protons in an element, then I have 4 AMUs. And so this number is also found underneath the element symbol on the periodic table. So that number underneath is going to tell us the mass of something. The mass number is also going to tell us atomic mass units. The only thing that's changing is the units. If somebody asked me to find the mass of beryllium, I'm sorry, I don't have my periodic table here, so let's do the mass of boron because I know it. The mass of boron, if somebody asked me for the mass of boron, I would say 11 grams. If they asked me for the mass number, I would simply say 11 because they just want a number. If they asked me for the atomic mass unit, I would say 11 AMUs. Okay, so do you see it's always the same number, the units just change. And so here's another example. Hydrogen has 1 proton and its atomic mass unit is 1 AMU. Okay, another one we need to talk about is atomic mass, also known as average atomic mass. This is when they take the isotopes of the same element, so that means that an element has 2 or 3 different forms because they have different numbers of neutrons. They take all of those, they figure out which one is most abundant, and they average the masses together depending on how abundant they are in the universe. So the one that's found most in the universe is going to be the one closest to the mass at the bottom of the element symbol. So this is the weighted average mass of the isotopes. This is what that's talking about. And this is the reason the atomic mass is not a whole number, because it's an average of the isotopes altogether. And this number is also found underneath the element symbol. So just like we talked about earlier, if I wanted the mass of boron, it would be 11 grams. If I wanted the mass number of boron, it would be 11. If I wanted the atomic mass unit of boron, it would be 11 AMUs. And if I wanted the average atomic mass, it would be 11 U, because U is the unit for average atomic mass. Now, I want us to practice before we talk about isotopes. I want you to find out how many protons each of these have. Use your periodic table and pause the video right now. Answer how many protons these have and resume to see if you're correct. All right, check your answers. Make sure you're correct. If you're not, try to figure out why. And if you have a question about it, make sure you jot it down so you remember to ask the next day. Now I'd like you to find the number of electrons for all of these. So pause the video and determine the number of electrons. All right, hopefully you got all these correct. If not, make sure you put a star next to it so you can ask me the next class we have. Now I'd like you to find neutrons. All right, I'm hoping you're getting all these correct, but like I said earlier, if you're not, jot down a question so we know to talk about it in class. Now, this is just a picture to show you the atomic number is up here at the top, okay, for germanium. So this means they have 32, germanium has 32 protons, 32 electrons. And then down here is the mass number. So 74, if I wanted the mass, I would say 74 grams. If I wanted atomic mass, I'd say 74 grams. If I wanted mass number, I would just say 74. If I wanted atomic mass units, I'd say 74 AMUs. Now, the atomic mass and the atomic number can be written other ways. For instance, sometimes we call this on the left-hand side max because the mass number is on top, the atomic number is on the bottom, and then the atomic symbol is to the right of both of those. And here's an example over here on your right of how that might work, okay? So it can be written like this, and you need to know how to take, if I gave you this, instead of using your periodic table, you need to be able to tell me how many protons, neutrons, and electrons. So just remember max. If it's written like this, it's going to be in max order, where mass is on top, atomic numbers on bottom. All right, let's talk about isotopes. Isotopes are atoms of the same element, so they have the same number of protons, but they have different number of neutrons. So here's an example of hydrogen. This is hydrogen 1, which is the most abundant we have on Earth, actually. That's not always the case. But then this is hydrogen 2. The only difference is we've added a neutron. And then hydrogen 3, we've added 2 neutrons. So all of these have different masses, okay? And what they do is they take the most common one and the percentage of it, and they calculate and average all of these masses together depending on the percentage or how often it's found in the universe. And that's how we get our mass numbers at the bottom. So the most common isotope is the one that's placed on the periodic table, but the masses on the bottom of your element are averaged all together, and that's why we have the decimal like we talked about earlier. Now, the average of masses is called the average atomic mass, and I think we talked about this earlier, the average atomic mass, and I was telling you grams, so I apologize. What the average atomic mass's unit is U. So if I asked you for boron's average atomic mass, then we would say 11U. The average atomic mass equals the mass number. It also equals the mass. We've already gone over that. The bottom number is all of these things. So it's time for our summary. And what I'd like you to do today is an Instagram summary. And so I want you to draw a picture that you could possibly post on Instagram that represents Chapter 4 video. All right, and I'll see you in class.